Welcome to The Explainer. Today we are taking on machine learning. And look, if you've ever stared at one of those cheat sheets, the ones just packed with jargon, and felt your brain start to melt, don't worry, you're not alone. We're going to take all that complexity and turn it into a clear, step-by-step journey. All right, let's jump right in with the most important question there is. How in the world does a machine actually learn? And we're not just going to throw a definition at you. We're going to build a model right here from the ground up, just using the concepts. So first things first, before you can teach anything, you need a teaching philosophy, right? And in machine learning, it really all comes down to two main schools of thought that dictate how a machine gets smart. On one hand, you've got supervised learning. The best way to think about this is like studying for a test with the answer key right in front of you. You show the machine a picture of a cat and you tell it, this is a cat. Do that 1,000,000 times and it starts to get the picture. Then you've got its total opposite, unsupervised learning. This is like dumping a giant box of Legos on the floor and just saying, sort these. The machine has to figure out on its own, okay, these are all red squares and these are blue circles. No instructions, just raw data. Okay, so we have our philosophy. Let's say we go with the supervised route. Now we have to make another choice. What type of model are we going to use? This is kind of like choosing the right kind of brain for the specific task you have in mind. And believe me, there are a lot of brains to pick from. You have your simpler ones, like linear regression, which is fantastic for predicting a number, like the price of a house. Then you have decision trees, which work like a big game of 20 questions. You can even get a whole bunch of those trees working together in what's called a random forest. Support vector machines are amazing at just drawing the sharpest possible line between two groups. And then you have the heavy hitters, neural networks. Each one of these has its own special talent. For our little project today, let's go with a neural network. These are the engines behind a lot of the AI you see today, from recognizing faces to translating languages. They're inspired by our own brains, with all these layers of connected neurons. And here's the really wild part. Any single neuron is, well, pretty simple. But when you get millions of them working together, they can learn to see these incredibly complex, subtle patterns that a human might never even notice. So we've picked our model's brain, a neural network. But a brain is pretty useless if it doesn't actually know how to learn. So now it's time for boot camp. We've got to put it through a training regimen. And here's a concept that might seem a little backwards at first. Learning starts with failure. Every single time our model makes a guess, we use something called a loss function to give it a score on exactly how wrong it was. You can think of it like your score in golf. You want that number to be as low as possible. The entire goal of training is to get that loss score down, as close to zero as it can possibly get. And that process happens in this constant four-step loop. First, the model makes a guess. We call that forward propagation. Second, we calculate the loss. We see how badly it messed up. Third, and this is really the secret sauce, is something called back propagation. Imagine a detective tracing the crime back from the result. It sends that error backward through the whole network to figure out which connections were the most responsible for the mistake. And finally, step 4, it adjusts those connections, we call them weights, just a tiny bit so that next time the guess will be a little less wrong. You do that 1,000,000 times and boom, that's learning. But here's the catch. Just like any student, our model can pick up some really bad study habits. The process isn't always perfect, and if we're not careful, it can start to learn completely the wrong lessons from the data we give it. This brings us to one of the biggest headaches in machine learning, underfitting versus overfitting. An underfit model, that's the lazy student who didn't even open the book. Their ideas are way too simple, and they fail both the practice questions and the final exam. But an overfit model is just as useless. That's the student who didn't learn the concepts, they just memorized the answer key to the practice test. The moment they see a new question on the final, they completely fall apart. So how do we stop our model from becoming that student who just memorizes everything? We use a clever trick called regularization. It's basically a way of adding a penalty for complexity. We're telling the model, hey, I want you to get the right answer, but I'm also going to punish you if your explanation gets too complicated. This encourages it to find the simpler, more elegant patterns that are more likely to work on data it's never seen before. Okay, so our model is trained. We've used some smart techniques to keep it from getting lazy or from memorizing. Now, it's time for the final exam. How do we give our model a final grade to see if all this work actually paid off? Well, the absolute #1 rule of this final exam is simple. No cheating. You can't test the model on problems it's already seen the answers to. So we very carefully split our data into 3 piles. The training set, that's the textbook it studies from. The validation set is like a series of pop quizzes we use to tune our strategy. And the testing set, that's the final exam. It's kept under lock and key, and the model only sees it once, right at the very end, to get a true measure of how smart it really is. Now, when you see this table, don't get intimidated. This is called a confusion matrix, and it's probably the most important report card you can give your model. Why? Because it doesn't just give you one grade. It breaks down every single prediction and tells you not just when it was right, but the different ways it was wrong.
Now, the most obvious grade is accuracy. It's super simple. What percentage of the time did the model get it right? But this can be so misleading. Think about it. If you're trying to detect a rare disease that only 1% of people have, a model that just guesses no every single time will be 99% accurate. But it's also completely, utterly useless.
That's why we need smarter metrics. Enter precision. Precision asks a really specific question. Out of all the times the model said positive, how often was it actually correct? This matters a ton when a false positive is a big deal. Take a spam filter. You want super high precision because you need to be really confident that an important email from your boss didn't get tossed in the junk folder by mistake.
And then you have its partner, recall. Recall asks the opposite question. Of all the actual positive cases that exist, how many did our model manage to catch? This is absolutely critical when a false negative is a disaster. If you're building a model to detect cancer, you need the highest recall imaginable. You'd rather have a few false alarms than miss a single real case.
And that's really the most important takeaway here. There's no single best way to measure a model. The metric you decide to focus on, whether it's high precision or high recall, literally shapes your model's personality. You are defining what smart actually means for that specific task. So there you have it. We've gone all the way from a basic idea to picking a brain, putting it through training, and giving it a final exam. We've really seen how a machine learns. And that whole journey, well, it leaves us with an even bigger, more exciting question to chew on.